Okay, so the first thing I have to do is thank you guys for coming. I was looking at the schedule about a week ago, and I was trying to figure out when do I actually, teach this, and I miscalculated dates, and I'm like, okay, great. So the evening I'm teaching, we have the NBA Finals, the Cavs are going to play Golden State, we have the NHL Finals, Pittsburgh is going to go for the Cup, we have the Jays starting the first place team in the AL East. So I sent an email to our HR, I'm like, can we just cancel the event? Like, do I actually have to come? But no, but only the NHL and the Jays are playing today, so who cares, right? I also want to give a shout out to my boot camp class who are here, spread throughout the audience. So every year at Infusion, we run a boot camp this time of year. So we have about 8 to 12 new graduates from various universities across North America, and we run a 4-week boot camp. And we teach them, fundamentals, web, and the idea is at the end of it, they can, start their road to consulting. So I was talking to a few of our executives who also have given them various, sessions and so forth, and we were all reflecting how energizing it is to talk to new grads because they're untainted by cynicism, They still think they can make a difference in the world. They don't know that there's this existential void that awaits them in middle-aged life and that everything is futile. So it is quite nice to have them here. All right, so we're going to be talking about a very cool topic, superintelligence, deep learning. It's really exciting stuff, and it's very relevant, and we'll see how it's relevant to practical things in mobile. But let's start off with what was considered a monumental achievement in the field of artificial intelligence a few months ago, and it's exemplified with this picture up here. So this created shockwaves not only in the artificial intelligence community, but really in the computing industry. First of all, does anybody know what this was and why it was so significant? AlphaGo. AlphaGo, it's right there. Okay, so what was it? What was AlphaGo and how did it work? Yeah.
First time a computer beat a human opponent, a master opponent at the game Go.
Okay, so it was the first time that a machine, an artificial intelligence computer, beat somebody at the master level, in this case the actual world champion, at the game of Go. This would be the equivalent of Deep Blue beating Garry Kasparov in 1997 in chess. Only actually, when you consider the underlying forces, this was actually a lot more impressive. Does anybody know why this was considered so monumental in the realm of AI? Even more than chess, even more than IBM Watson, and some of AlphaGo's predecessors. What was so impressive about AlphaGo's triumph over, Lisa Doll in this case? Yeah.
Something like there are more possible positions than atoms in the universe or some monumental.
Okay, so there's more possible positions in Go than atoms in the universe. The same thing could be said of chess. If you look at the number of board positions that there legally can be in chess, if you actually iterate it all through through the end of the game, you get the same kind of number. More positions in chess than there would be atoms in the universe. So it is at least as complex as that. But is there anything else?
Is it more about branching or something?
Okay, so the branching factor is a lot more significant. Okay, and what does that mean, first of all? The branching factor in AI is basically how many moves on average you have at your disposal as a player. Right? So of all the possibilities in front of you, how many moves can you make? In chess, the branching factor is about 35. And so if you consider a brute force approach, I have 35 moves, you have 35 responses, I have 35 responses to that, the numbers get exponential pretty quickly. And I think after something like 10 moves in chess, you have something like 14 billion board positions. However, the branching factor in Go, as you see here, is about 300. Okay, so Go is played on a 19 by 19 board. I place stones on it. And so the branching factor in Go is an order of magnitude higher than chess. And so the approaches that were used with Deep Blue, exponential searching, really powerful hardware, make no sense for Go. Okay, prior to about 5 years ago, the best Go computers could approach the level of a strong amateur, and that was it. So first of all, they thought this wouldn't be traversed or scaled for about 10 or 15 years. I'm actually reading a book now on superintelligence by Nick Bostrom, and in the introductory chapter, he goes, maybe we'll conquer Go, at the end of 2020. And so that was published about a year ago. Little did he know in a year we'd actually conquer it. So that's the first thing. The branching factor, the complexity of the game goes well beyond what we have with chess. What else? Okay, experts weren't predicting a breakthrough for decades. Probably what is most significant about this, though, was the way Google, in this case DeepMind, which is a subsidiary of Google, approached the problem, using neural networks and deep learning. And as we'll see, the innovations and kind of the underlying approach they took with AlphaGo applies to other learning techniques as well. Okay? So let's back up for a second and try to understand neural networks. And for those of you that took CS or engineering in school, this will be a little bit of a review. So a neural network is simply a computational model that emulates the structure of the brain. In the early days of AI, okay, the 1950s, scientists believed that computers had to emulate humans. They had to emulate the way we think. They had to really, model their thought process after the human brain. And they eventually abandoned that approach for circuitry and raw computational power and so forth. What's ironic with neural networks is that we are coming back to the original vision that the fathers of AI had almost 50, 60 years ago. So to understand neural networks, we of course have to understand something about the human brain. Okay, I never thought you'd see this, the human biology of the brain in a engineering lecture. So your brain is probably one of the most awesome devices in the cosmos when we look at what exists in the universe today. It's a 3-pound packet of tissue, a warm, wet biological structure that has about 100 million neural cells, or neurons as we call them, about 100 trillion connectors, axons that connect those cells, and synapses that kind of connect onto those neurons. Yeah?
Sorry, there are 100 billion neurons.
100 billion, isn't that what I said? Did I say 100 million?
Sorry,
I meant 100 billion, and there's trillions of connectors. Sorry, yeah, order of magnitude higher, I should have been. Yeah, so 100 billion neural cells and connectors. Now, there's a discipline, an obscure discipline of neuroscience called cognitive neuromodeling, which basically posits that when you think of something conceptually, okay, the imprint in your brain, the neurons that are firing to make that thought happen, roughly reflect what you are thinking about. Okay, in other words, if you think about a pencil versus a pen, the neural activations should be somewhat similar, as opposed to, say, thinking about a pencil and, a hockey player, which would be a little bit different. To illustrate this, let's try a little exercise together. So here you have a gender-ambiguous face that is sandwiched in between what we call hyperbolic faces, so faces with strong features, right? The theory of visual science tells us that if I ask you to stare for 10 or 15 seconds at this male face, okay, which I encourage you guys to do right now, and then I ask you to interpret the gender of this face, most of you will say that it's female. Okay, let's try the reverse. If everybody stares at the female face for 10 or 15 seconds, and then you stare at this face, most of you, not all of you, most of you will interpret this as male. All right? And this basically occurs because as you start staring, that neural activation pattern becomes a little more pronounced, and so when you are shown an ambiguous face, your interpretation actually occurs in the reverse direction. All right? So a neural network, then, is simply a virtual kind of construction that models our brain. Okay? There are inputs, and there are outputs, and there's all this, junk in between, not junk really, stuff that really models how we think conceptually. And so this modeling, starts to approach the complexity of the brain. It allows artificial intelligence machines to do some amazing things. All right? Let's take an example. So one of the challenges of, let's say, computer graphics and visual recognition was actually recognizing objects. All right? So if you think about 20, 30 years ago, to actually write an algorithm to say that this is a dog, okay, knowing that it's a dog, was extremely difficult because it was so hard to do mathematically because there are so many variations with what is considered a dog, right? It's quite amazing when you think about it. You can give a 5-year-old a picture of 10 dogs, And with ease, right, they'll be able to tell you exactly what that picture contains. Try doing the same with a machine at least before 5 years ago, and it was almost an intractable problem. It was very, very difficult to do. So how do we start to approach a solution here with neural networks? Well, the first thing to realize is that we can break down this picture into a number of pixels. And the relationship of these pixels will generally tell us something about the makeup of a dog, okay? So a dog has certain characteristics with respect to the size of its nose, with respect to how far its eyes are, with respect to how its pupils are dilated, right? And we would expect different characteristics if we had the exact same matrix with a cat, let's say. So let's assume for a moment that all these pixels with different numerical values were inputs into a neural network. Right? So that neural network diagram I showed you at the beginning, we have all these input parameters, we have a number of levels, it goes through some calculations, and we have outputs. And let's say I wanted the output to simply be a true or false value to tell me whether or not something was a dog or a cat. Right? So I start giving the neural network a lot of data, and the amazing thing about it is that I start propagating these values through my network. Right? So I have thousands, sometimes millions of layers in the network, and just as in your brain, okay, you have neural signals which are amplified or are mitigated depending on what you're thinking about, we do the exact same thing in a virtual way. Okay, we have weights on the various layers. They are sometimes nonlinear in fashion or sometimes linear in fashion, and we run through this data on the neural network. Now here's the big challenge with the neural network, and here's where the learning aspect of neural networks comes into play. What is the weights or the numerical amplification that you set for all these layers to get the answer that you want, right? If we were to set this randomly, for example, and then we were to simply propagate all this data through the network, we would get statistical junk at the end of the day, right? So if I gave something a picture of a dog and I broke it down, I would probably get it being identified right, 50% of the time versus a cat, right? It would be almost random. But here's the key insight into neural networks and artificial neural network construction. I know as a human, when I feed the picture to the neural network, whether or not it's a dog or a cat, right? I know the answer ahead of time. So what if I knew the answer I'm expecting, and then I worked backwards to actually figure out what my weights were? Okay, this is called a backward propagation pass. And so I work backwards in this sense, and through this iterative process, I can start to set my weights correctly. Now, I wouldn't do this with one picture. I would do this with thousands, if not millions. And this is where the magic of neural networks actually comes from. By doing this, hundreds of thousands and millions of times, the network eventually will get very good at recognizing dogs. And it's kind of a mystery. It's quite amazing. We know the mathematical setup of neural networks. Okay? We know how they work. We can program them. We're getting very sophisticated in terms of the mathematics behind them, right? But we don't know why the certain combination of weights will actually tell us whether or not something is a dog or a cat. In the same way that we really can't tell you, neuroscience can't tell you why your brain triggers the way it does and why you recognize something as a dog or a cat. You show a child a picture of a dog or a cat, they'll be able to tell you what it is. Ask them how they came to that conclusion. Again, I tried this with my 5-year-old niece. She just said, I don't know, it's a dog. Like, what's there to really think about? Okay, and that is really what is incredible about neural networks. The reason we call this deep learning is because in practice, these neural networks are in fact have millions of parameters, sometimes billions of parameters with many, many layers. Okay, and that is where the term deep learning comes from. So what we are in fact doing with neural networks is we are taking a copy, approach, or a imitation by flattery approach, where we don't know why the brain works, we just know that it's very effective for us, and we have replicated this structure virtually to try to mimic what the human brain is doing. Okay, and by subjecting these networks to a training data set that is very, very large, over time, we can start to train the network to do some remarkable things. Okay, now as I mentioned, the mathematics behind neural networks is where you really get into the nitty-gritty. And this is where some of the significant developments have occurred over the past, let's say, 5 years. Right? Given the promise of neural networks, which are in large part fueled by the raw computing power we now have for machines, right? Cloud computing, machines that can actually implement neural networks with billions of parameters and several layers deep. The mathematics behind this have become quite sophisticated. right? So if, for example, I take a look at a simple neural network that interprets a 32 by 32-bit image, and I want an output vector where I'm going to classify that image as one of, a number of things, most often than not, some of the weights in between my neural network or the hidden layers will be nonlinear in fashion, right? And that is really where the tweaking and the expertise with neural networks comes, right? A lot of the foundational theory behind neural network design, that is pretty firm. Where people are experimenting now is with the mathematics behind them, and that is what is really innovative, okay? So if we return back to AlphaGo, okay, what was amazing about AlphaGo was how they actually conquered the problem of Go. And so they actually used two neural networks to implement AlphaGo. They actually used a value network to evaluate board positions and a policy network to select moves. All right, and they actually augmented that with another technique that has proven extremely fruitful in artificial intelligence and gaming, and that is a Monte Carlo search tree. Right? You guys probably have encountered Monte Carlo simulation, where if you have a nonlinear problem, you can often make it linear by simulating it randomly and actually figuring out what your data set looks like. And so what the computer actually did was it took these two neural networks, it basically added Monte Carlo simulation where for each plausible move, the computer played out millions of games depending on that move, and then statistically it would know that this value would result in a greater chance of winning. And finally, what Google did was they actually developed specialized hardware for this. Okay, so it's actually something called a tensor processing unit, or TPU for short. So the structure I showed you, a neural network, right? They used to simulate that in hardware, like a node and the weights and all that. That would all be simulated in software. They are now actually building hardware, specialized hardware, to implement certain types of neural networks. And so effectively what they're doing is they're creating silicon equivalents of the biology of your brain, which is quite incredible. And so you combine all these things together. To me, it's amazing the human even won one game. And he admitted that after the fact. At the beginning of the contest, nobody really knew how strong AlphaGo was. He predicted that he'd win 4 games to 1. He ended up doing the reverse. He won 1 game, and he lost 4, and he was happy he even won a single game. And the thing that's scary is that AlphaGo will learn from that encounter. And so if he played it again, would he even win a single game? And they are, trying to set that up, not with him, I think with a Chinese counterpart who most people think is actually stronger, but not currently the world champion. So it'll be interesting to see what happens with that. Okay, another interesting aspect of deep learning and AlphaGo was that AlphaGo was subjected to a rigorous training session, or 2 of them actually. Supervised learning, in which case the network was calibrated by playing through thousands of master games, right? And then reinforcement learning, where it played itself to further polish its neural weights. The analogy I like to give here is that of The Matrix. Okay, you guys have seen the movie The Matrix, where Keanu Reeves, they plug him into a computer and he goes like this, and all of a sudden he's learned karate in like 60 seconds, right? And then the other guy's like, show me, and they play karate. That's sort of what AlphaGo is doing. It's learning like a lifetime of learning in, a matter of seconds, at least in terms of our processing power. All right? Now here's the fascinating thing about the learning capabilities of AlphaGo, is that if this seems analogous to how we master particular skills, that is through supervised learning, through rigorous schemes where our neural weights are polished, that's because it is, believe it or not. All right? There's a fascinating book by a guy named Daniel Coyle, and he wrote about very high achievers. All right? He wrote about Lance Armstrong, for example, before Lance Armstrong, did his whole thing. And what he wanted to do was figure out how people got so exceptional at what they were doing, right? He basically went to Brazil and he said, a disproportional amount of amazing soccer players come from this little slum in Rio de Janeiro. An amazing amount of, tennis players come from this part of Russia. For some reason, high musical achievers come from upstate New York. So he wanted to find the commonality between all those situations. And he basically came up with an idea called deep practice. So what he said was deep practice is built on a paradox, struggling in certain targeted ways, operating at the edges of your ability, where you make mistakes makes you smarter. Or to put it in a slightly different way, experiences where you're forced to slow down, make errors and correct them as if you would if you were walking up an ice-covered hill, slipping and stumbling as you go, end up making you swift and graceful without you realizing it. And he actually determined a biological basis for this hypothesis. Okay, there's a substance called myelin, which is a substance that insulates your neural circuits and increases the speed at which certain signals propagate. What they have found is that when you undergo deep practice, the myelin around certain neurons in your brain actually increases and makes those neural bonds stronger. Right? And so this is why when people say, like 10,000 hours of practice really makes you an expert at something, it is not, speculation. There is actually neuroscience that sort of shows this. And so this leads to an illusion. You think that you're naturally gifted at something, and a skill once gained feels utterly natural, as if it was something we were always possessed, when in fact we didn't. Okay, think about something as effortless as even language, right? Speaking in your native tongue. There was one time in your life where you couldn't do that. We don't even think about it, right? So I just want to go over a quick tangent here, because I just find this a fascinating topic. When Coyle's book came out, a lot of people used it as evidence that with enough practice, you could really accomplish anything at the world-class level, with enough practice, right? They interpreted his findings like that. And so, as my class knows, I'm a huge sports fan, right? NBA, soccer, I mean, there's so many things going on, I don't even know what to do with myself. My favorite tennis player is this guy right here, Roger Federer, right? I have been fortunate enough to see Roger Federer play tennis twice in my life. I saw him play twice at the US Open. So I saw him play in 2007 against Andy Roddick in the quarterfinals, and I was actually lucky enough to see him last year play Djokovic in the final, in the US Open final. And it was actually kind of a reverse experience in each case. In the first game in 2007, and most people think Federer was at his absolute peak at that point in his life, you always got the feeling that Roddick, who was also playing really well, was just hanging in against a better player. That he was giving it his best, but he just, wasn't quite going to beat him. And it was the reverse feeling that I had when I saw Federer play Djokovic last year. Like, he was giving it his all, he was a half step slower than he was in 2007, and although he won a set, you just kind of knew Djokovic would win in the end, right? But from the first match, there was a little excerpt, because I watched it on TV the next day, that really caught my attention. I'm going to play you a quick excerpt from this match. Whoops. Hold on.
And that's the little bit of genius that Federer has that Roddick just won't ever have. Yeah.
Did you guys catch that, what the commentator said? That's the little bit of genius that Federer has that Roddick just won't ever have, right? And it was almost instinctual. It's not like the commentator really reflected on that. What was he trying to capture? He's trying to capture, there's something ineffable about like just world-class ability. And I thought of that after the 2012 Wimbledon final between Roddick and Andy Murray and Roger Federer. That was Federer's last Grand Slam. And there was two different excerpts from the newspapers, right? The first was written by a British journalist from the Telegraph, said, "Talent does what it can, genius does what it must." The old Edward Bulwer Lytton aphorism smacked Andy Murray round the head in the first Wimbledon final, his fourth in Grand Slam tournaments overall. Murray was good as he could be. Federer was the master we always knew he was. This was an explainable defeat to the greatest of champions. Genius, it does you in. And then somebody else wrote, and this is a guy who does a lot of work in chess, world-level chess, and he wrote, "Although we tend to think of genius as something akin to magic, a kind of shortcut to mastery of the elements, it is nothing of the sort. A proper investigation of the careers of supreme achievers, whether in sports or other fields, reveals that they are based above all on a monomaniacal diligence and concentration. Constant struggle, in other words. Seen in this light, we might define genius as talent multiplied by effort." Okay, and I show you this because we're going to talk about creativity a little bit later, and these are two sides to the coin. Some would say it's intrinsic, some would say it's nothing but work. I'll leave you guys to determine what the reality is. Most people would say it's in fact something in the middle, right? Is that at the very highest levels, you have multiple people working 10,000 hours in their lives, probably more, and at that level, it is the smallest sliver of ability, genetic ability, that makes the difference. Okay, so there are some obvious parallels between deep practice in the human realm and deep learning in the virtual realm, right? By emulating the former through the latter, we've succeeded in creating machines that crudely approximate how we think. although they cannot match the complexity of the brain yet, because our brain is still much more complex than even the most complex neural networks, density-wise, component-wise. They make up for in speed and endurance, right? And so this is why AlphaGo doesn't have the sophistication of Lisa Dahl's brain, but it can analyze almost every game of Go that's been played ever in a matter of hours, right? And that is really what machine intelligence compensates for in terms of its lack of sophistication. So we, in fact, have numerous types of neural networks in practice. Okay, we have convolutional neural networks, recurrent neural networks, long short-term neural networks. Probably the one that's gotten the most amount of theoretical attention today is the first one, convolutional neural networks. And they are now starting to do some incredible things using the apparatus I've described to you. So for example, they can recognize objects. Okay, given an object, a neural network can, using its training, and it's been trained through millions of images, tell you with a certain probability what that image is. And so this is Google's neural classification one, which given some pictures here can give you a certain probability of confidence that this is a certain image, right? So a motor scooter, a ship, a leopard. Okay, I didn't know whether this was a leopard or jaguar, and it has a better understanding than I do. And so what it does is what I said before, right? It starts at the macro level. It starts basically breaking up this image into pixels. Those are inputs of the neural network. And as we get down to the layers, it starts unwinding the relationship between these pixels. And through training, it'll be able to say that on average, this is what a leopard looks like. On average, this is what a monkey looks like. And because I've seen 2 million of them, if you give me a picture of one, I can tell you that this is a monkey with 99% probability. Here's another thing machines have been able to do, and that is, given an image, tell you what it is in colloquial English. So this is actually 2 neural networks. Okay, this is Deep Vision, a system from Google. And so, here it is actually giving you a picture of, let's say, a dog in the grass, and it'll tell you these are 2 dogs playing in the grass. Right? Did you ever notice with CAPTCHA images now, they're getting a lot more sophisticated when you buy tickets on Ticketmaster? Some of them will say highlight the pictures here that are of lions, and they'll show you a lion hiding in a tree and stuff. That's because it's computationally harder for computers to do that. It wants to make sure that you're a human. It's relatively easy for us to do. It is harder for a computer to do, but they are starting to do that. Okay, so I actually wanted to show this in practice. So these are all cloud APIs that you can leverage now. That given an image, it'll tell you with certain probability what this is. Google Vision's API, okay, which you can use right now for free, you can give it an image and it'll give you a breakdown of what it is. So here's the sample image they provide, and you can see Google's classification there on the right with an approximate probability. Okay, 98% chance that this is a pet, a 97.9% chance it's a dog, 96.1% chance it's a mammal of some kind. Okay, I gave the same image to IBM's Alchemy Vision. This is along the same kind of AI that powered Watson, and you can see the breakdown here. Okay, this is an animal, it's a mammal, it's a dog, and then after dog, I lose my probability. Wolfram, okay, also just released for free. You can try this on the web. It's image classification project. And so it identified this as a Cocker Spaniel. So I thought, well, this is great, but this is the sample image that everybody gives you. So what about real images, right? So I went to Pittsburgh for the long weekend, about a 5-hour drive from Toronto, and so I had a bunch of pictures from that. And just this afternoon, I decided to pick some and to see how the image classification technique would work. And so as you'll see, we have a lot of work to do still. Okay? This is a picture of a drink, and it thought it was a substance. I mean, it is a substance, but we expect a little more specificity, right? This is my dinner one night, pasta and some bread, and it classified it as a dish. I don't know if it meant like a physical dish or a dish that we eat, but it said it was a dish. Okay. This is, I don't know if you can see it, this is outside PNC Baseball Park. My wife here is imitating a statue of a player, right? Just a fun pose. And so I gave this, I was really curious as this would be, it thought this was a shopping center. Which you can sort of see, right? It sort of looks like maybe the parking lot of a shopping center. All right, so it didn't get that one. This is me outside PNC Park. Hey, it got it as a ballpark. Not bad. Okay, look at this. This is the mascot running up and down. Incidentally, So we went for the long weekend. The game was rained out on Sunday, so they rescheduled the game, I don't know why, for Monday afternoon. And most people in the States worked, so there's about 1,000 people in the ballpark. It was absolutely empty. So what did Wolfram think this was? I thought it was a boxing glove. I don't know what. Like, maybe this is the boxing glove, or that's the boxing glove? I'm not sure.
So all
Dan.
the tests were Wolfram?
Yeah.
Did you compare them to the other APIs, like Google Vision versus Wolfram?
So I haven't done Google Vision versus Wolfram. I'm going to try that. Okay, and the final one. Does anybody know, first of all, what this is? What's that?
Peanut roasting.
It's a peanut roasting, like, machine. So I don't even know how you would classify this. You show this to a human, they would just say, yeah, it's a thing that makes peanuts and turns. And so it thought it was a switch. Okay? The thing they actually found, so they actually did a classification experiment where they gave images to 5,000 people and then gave Google's AI the same task. And it found that Google was more accurate with like some important caveats. So if I showed you a picture of a leopard, most of you could tell me it's a leopard, but you wouldn't be able to tell me the subspecies or the subtype or whatever. But it found that when the AI was wrong, it was fantastically wrong, right? Like you would show it a picture of like, a dump truck and it would think it was a dandelion, right? So even with all the training, there's still a lot of work to do, okay? Some of the other things that, deep learning artificial neural networks can do. They can play video games, and that is, they play video games not by being exposed to code or rules. They simply are given video games. Here's the inputs. Here's what you can actually do in terms of pressing buttons. And here's the output in terms of levels. So it simply times the inputs so that eventually you can play the game at a master level. And it doesn't have to have any prior knowledge of the game. Okay, so it became an expert at playing Atari games because the inputs to them are actually quite simple. They can dream. What does this mean? Neural networks can dream. What it means is this. If I train a neural network through millions of images to recognize a lion, what would happen if I gave a neural network noise and I said, based on your neural weights, imagine a lion for me, or extrapolate this input to a lion? What do you think a lion looks like, given that I've trained you with 1 million of them? And so look at these results. They're fascinating. Okay, so you can see, for example, an ant. This is what a neural network thinks an ant looks like, right? The eyes are big, the body's small. A starfish sort of has this behavior, right? A parachute, a banana. Fascinating. Okay, and they can also dream in 3D. And so here's a video. I don't know if I actually embedded it in the PowerPoint presentation. Here's a video that some PhD students did of an ant colony, of actually diving into an ant colony just given what it was trained to do. Okay, another really cool thing that they've done, and you might have seen this. This is all over a lot of the AI blogs, is inceptionalism. So inceptionalism is a neural network's ability to basically combine two images and extract their relevant DNA to produce a mind-bending third. Okay, so these are two images on the left, and given that, the neural network can produce something like this. Cool stuff, eh? Okay, let's come back down to earth just for a tad. And let's talk about some practical applications of these. And then we're going to go back into pie in the sky stuff. Probably the most relevant thing, I would say, in the enterprise and mobile and so forth, where you are seeing the effects of deep learning research and systems and so forth, is with bots. Okay, and we're actually starting to do some work in this area, and it's fascinating. The way to think of bots, and I really like when someone phrased it this way, is conversation as a platform, right? So we are used to human interfaces to computers being, mouses and keyboards and electronic devices, right? It was fascinating. I don't know if you guys have seen this on YouTube. They give a bunch of 5- and 6-year-old kids now, they put them in front of an Apple IIe computer, and they try to get them to figure out how to turn it on. And most of them start touching the screen, because that's what they're used to, right? Well, we are envisioning a time now where human language is the user interface, because natural language processing and contextual understanding has reached a certain level of sophistication. And so bots are the apps for this new paradigm. All right, so they, in fact, what we say is they reverse the paradigm. Whereas before we had to adapt ourselves to machine, we had to learn how to type, we had to learn the mouses, you had to learn context and all these things. Computers are learning our natural interface, our conversational patterns. You can say what you want, it'll understand you, right? Something that you can actually ask a question of in colloquial, regular English with all its idioms and ambiguities, and it'll understand. And there are numerous types of bots: entertainment bots, utility bots, customer bots. All right? Bots actually have a fascinating history, believe it or not. The first bot, which some of you may have heard of, was Eliza, which was published in 1966. And the history of this is quite interesting. It was created by a computer scientist / psychologist who created the system for people who were lonely. And it was a system that would reply to your inquiries and questions with generalities, right? You can find it online, and you'll say something like, "I had a long day. Tell me about your long day." When it didn't know what you were talking about, it would say, "Go on," right? It was really skilled at just getting conversation out of you. My wife sometimes accuses me of doing that when I'm not really listening. Those were the first ones. Now, what are some of the challenges with bots from a practical perspective? Well, first of all, it's new to us. Most of us aren't used to conversational English being a platform. When we show this to most adults, they are all phased out. What can I say? How do I say it? Children just start talking. And so you can imagine a day where your toddler will get used to the idea that this is an entity that he or she can talk to and be understood. The best practices around this are still evolving. Language patterns are still tricky. Probably the most difficult one is context, right? It doesn't always know who you are or what you want or your financial history. So there is a problem of contextual understanding that is still a limitation for a machine. All right? And now an important distinction in this world is the distinction between a bot and an agent. All right? A bot represents an entity that represents a third party who you can query for information. So imagine a bot for Air Canada. And you could ask it, what is the cheapest flight you have between Calgary and Toronto between the dates of August 4th and August 7th? I want to fly direct, and I want to be able to use my Aeroplan points. Right? So it'll take that, it'll convert it into discrete bits of information that it can query and actually give you an English answer for. And so that is the power of bots. And you could say things like, are there any hidden costs? How many pieces of luggage could I have? Right? An agent is like a personal assistant acting on your behalf. Have you guys seen the movie Her that came out maybe 2-3 years ago? Won, best screenplay for Oscar. Fascinating movie where this entity that exists on this individual's phone is a personal assistant for Joaquin Phoenix in this case, right? And says, do you want me to make reservations for you? It knows your context. It knows what you like. It knows your preferences. It can act on your behalf. And you are seeing a very powerful agent, probably the most sophisticated one we've seen in Cortana, which is packaged with Windows 10. Siri was probably a predecessor to that. All right? And so bots represent services. Agents act on your behalf. And so you can just imagine the opportunities here in terms of customer service, in terms of tutoring, education. There's just so many things here. And there are frameworks that are now developed or being developed to support this. One of them is the Microsoft Bot Framework, which is built on Azure Machine Learning. Okay, well, we're actually doing some experimental versions of this for some of the banks we work with. All right, one of the things we're developing is a tool that you can ask natural language to that will figure out an investment strategy for you. Right? So instead of having a multiple choice type of questionnaire that is really ungainly and long to fill out, you can simply say, these are my investment goals. I have 2 kids that are going to be going to college in 20 years. This is how much my income is. What are my options, right? So we're working with, the Microsoft Bot Framework to actually develop a natural language interface. And the way we can do this is primarily because of the, developments we've seen with deep learning and machine learning and things like that. Okay, so some fascinating developments here, and definitely something to keep an eye on. This is not something that'll be, something you're going to see in 5 years. This is things that are in development right now. Okay, there are beta versions of these frameworks that are out there. IBM has their Watson API, which is effectively the Watson natural language processor that's been put in the cloud. Google has similar natural language capabilities. So you can just imagine where some of these cloud-based offerings are going. Okay, back to pie in the sky stuff. it's amazing that the bar for what is considered artificial intelligence now is steadily being raised with time. At one point, people said that the minute we have a computer that can play world championship level chess, that will be true, consciousness in a machine. And that happened in 1997, and everybody said, well, that's chess, and Deep Blue can't do anything other than play chess. In fact, Deep Blue doesn't even know it's playing chess. It doesn't even know it's the best player in the world, right? And then it was AlphaGo. And then it was like, can it understand English? And then it, beat everybody in Jeopardy. So the bar for what is considered achievement in artificial intelligence is steadily getting higher. And many people feel it's culminated in creativity. Okay, if a machine can show creativity, that will be the standard. So let's discuss that. First of all, does anybody know what this is a picture of? What? Picasso, yeah, this is a Picasso. Of course, this is his distinctive style. Does anybody know what this painting is or what it's called?
The bathers.
Wait, what?
Bathers?
Bathers?
Bathers.
Bathers.
Bathing or swimming or something.
Okay. It's the women of Avignon. And I'm not going to try to pronounce it in French. And this came out in 1908. Interesting aspect to Avignon. I don't know if any of you, from a historical perspective, this is just a fascinating city because it was where the papacy relocated in the 13th and 14th centuries. So Picasso created this in 1907 and 1908, or between that time period, and it was a revelation when he came out with this painting. It's been considered probably one of the most significant paintings in art history. And it inspired a whole other development of painting known as Cubism, where the art forms and their weights basically took on the aesthetic significance of the painting. So the question that people are now asking is, okay, you can give a machine 1,000 pictures of a dog and it can tell you it's a dog, but you need to give it those pictures. Yes, a neural network can take 2 pictures of art and produce another piece of art that looks good, but it needed that inspiration in the first place. Can a computer really create? Can it do something that is fundamentally new? Right? So can it, imagine? Is there a level of genius behind it? And what are we trying to say when we use these nebulous concepts? Right? Creativity, someone said, is the mind's capacity for self-reflection, self-reference, self-comprehension, the dynamical and fluid creation of concepts and association. Genius is the fire that lights itself, said somebody. Originality, imagination, the self-driving ability to set one's mind free of the worn channels of tradition. Right? The creators of our world, and Karen Armstrong, who's a writer, came up with a huge description of what she thought creativity was. Okay, it's in some sense intuitive. You're letting go. So can a computer do this, is what people are asking now. I don't know if you guys have ever heard of Howard Gardner. Howard Gardner was a psychologist who studied multiple intelligence theory, or actually was one of the founders of multiple intelligence theory. Does anybody know what this is, multiple intelligence theory? MI, as it's known in psychological terms? Yeah?
I don't know the exact definition, but it's mainly used in education.
Okay, it's used a lot in education, absolutely.
It suggests we have like 7 or 8 different kinds of intelligence.
Yeah, it's the suggestion that the traditional definition of intelligence, the IQ test and all that, was developed in Eurocentric terms, so logic, mathematics. And Gardner said when you look at people, when we use the term intelligence, they can actually have high facility in numerous things. Okay, and so he basically compartmentalized intelligence into tranches. And so he said, there's spatial intelligence, musical intelligence, kinetic intelligence, intelligence with the body. And this is actually used in education now. They'll actually try to identify multiple intelligences in individuals and try to think of careers that are connected to them, which is fascinating. So this individual, anyways, Gardner, basically studied high creativity people. He looked at Freud, Einstein, Picasso, and what he found was that they were uniquely creative because they had a very high intelligence across multiple disciplines. And they were able to fuse those disciplines in a unique and fundamentally new way. So Einstein, for example, not only had a very high mathematical intelligence, but he had a very high spatial intelligence. And it was that spatial intelligence that allowed him to think in multiple dimensions and come up with things like the theory of relativity and so forth. Okay, so now the question, guys, can we automate creativity? Can we have a machine that is creative? What are some of the problems? How do you give a machine intentionality? right? How do you give it some motivation for something? Our CEO thinks that all this talk about superintelligence stuff is ultimately futile because you may create a superintelligent computer, but it won't want to do anything. It'll just want to sit on the couch and say, yeah, I can solve all the world's problems, but I don't want to. I'm just going to sit here. What's that? It will if you threaten to cut the power. And then we have, the Terminator series being unleashed. And it tries to kill us, yeah. Okay? So here's the thing. There is a branch of AI now called computational creativity. And this is an area of AI where we try to, for lack of a better word, dissolve creativity into quantified parts and get machines to be creative. Now, here's the fascinating thing. When we say that machines are creative to whom or what? Right? We judge a piece of art as creative as humans. So some people think when you have a machine eventually of extreme intelligence, it'll create things that are creative to us, but it might actually have to dumb down its outputs to do that. It might have a painting that is remarkably creative to itself, but not creative to us. So that's an interesting question. People say that genuine creativity cannot be reduced to a computational process, and there are scientists and researchers now who beg to differ. One of the areas is something called digital synaptic neural substrate, a very fancy term. And so what this researcher has done, and this group of researchers have done, they basically posit that creativity is the byproduct of poorly managed bits of information in your mind that mingle in ways we don't understand. He said, how many times have you heard an artist say, I painted this because I heard a certain song, or I saw a picture of an old acquaintance or an old lover, and this inspired this. So this was kind of the motivation for DSNS, where basically what this individual did was he took creative objects in various domains and broke them down into almost hash maps of those creative objects. And using an algorithm, he came up with a creative difference between them, and then searched for other objects with the same creative difference and generalized that into an actual creative object of value to us. Where he's done his most research is in the realm of chess problems. So computers have already conquered chess. They can beat most grandmasters. You can get an app on your phone that'll beat every player in the world. An area of chess that has yet been unexplored by most computers is the creation of chess problems. So this is the setting up of board positions like this and saying, white to play and mate in 3 moves, guaranteed. And these positions have a certain aesthetic quality to them in terms of, they'll have a position that you wouldn't normally see in the game, and there's a certain beauty associated with these designs. Okay, both these problems were created by a guy named Sam Lloyd, who's the most celebrated problem creator in the history of the game. So the DSN approach has been successfully applied to the realm of chess problems. And so here's an example of the program this individual wrote that actually will use inspiration from other domains to create a chess problem of aesthetic value to human beings. And so it's actually doing this in real time. He actually captured his program, setting up a board position, and it was inspired by paintings. And here's the thing that he found that was fascinating. He actually found the quality of the problems would be better if the quality of the paintings was lower. If he gave it like Renaissance art and things we would consider high art, it wasn't very good. If he gave it finger paintings by kindergarten kids, it was. He doesn't know why, he just knows that it works. Okay? So DSNS is one area where we are trying to delve into the world of computational creativity. And so imagine 5 years from now combining this with the sophistication of the neural network between AlphaGo. I mean, can we doubt that in time computers will be able to emulate us in what we do? Some other interesting contests. Okay, there was a contest at Dartmouth College just last month where they challenged AI exponents to basically do one of 3 things: to produce a story, an actual story on a topic that could be published in the New Yorker, to produce a poem, and to produce like a DJ set. And it would be considered a success if the expert judges couldn't tell whether or not it was human or not human. And the result was it failed. Okay, so there was no program yet that was as sophisticated so as to create a piece of literature that couldn't be interpreted as machine-made. And if you read this poem, which was one of the products of it, you can probably see why. People picking up electronic chronic, the balance like a giant tidal wave, never feeling supersonic or reaching any shallow grave. This is something somebody would write after a experience with certain substances, let's say. Okay? The final thing they did was there's this robot art competition where the basic purpose is to get a robot, a machine, to actually create physical art. And so here was the results of that contest, okay? This was first place by the team from National Taiwan University. And this is a machine that's basically mixing the colors and actually painting. This was second place, George Washington University. I mean, not bad in terms of the fidelity, in terms of actually creating an artistic, piece of work. All right, final section. Where this is all leading, most people think, is with something they term superintelligence. And that is, a conscious thinking machine, first of all, that is conscious. And number two, once we achieve that will exceed our own intelligence. And so the first question that people are grappling with is, what is the basis of consciousness? What causes you as an individual that's made up of matter and molecules and quarks and leptons and all these other alphabet soup of things to be a conscious mind, right? Neuroscience still does not understand the basis for consciousness. In fact, it's so ambiguous that the entire discipline is called the neural correlates of consciousness. And we don't understand why the combination in your brain gives you your ability to think the way you do. We just don't understand that. And the question that people are grappling with now, and you can see all the different, theories that have been hypothesized. People think it's a magnetic field. People think that it's quantum capabilities. Okay, Roger Penrose really plays in this area. And of course, some people would say it's spiritual or metaphysical or religious in nature. So the question that this will ultimately lead to is, can a silicon construction be conscious? Right? They say software, we have wetware, is what somebody said. Right? Can we actually create something that is conscious? And we simply don't know the answer to that. There are some people who posit that when you create a neural network that is sufficiently complex as we are, that it will just become self-aware. And there are other people who think it's more mysterious than that, and eventually it will happen, and we just don't know how. And that is ultimately where this kind of stuff is leading, right? Now, you may have heard of something called quantum computing. This is another talk I give. This is the idea that we can use quantum mechanics to actually implement computable processes. Some people believe that it's actually quantum effects in the mind that give us consciousness, and that quantum computing will be the key to unlocking that, okay? And we don't know if consciousness can be reduced to computation. And that is, I think, ultimately the big question that deep learning eventually will lead to. Okay, there's a fabulous book on this called Superintelligence by Nick Bostrom that kind of gets to these answers, all right? Okay, so just to wrap it up then, deep learning is basically realizing what the fathers of AI tried to realize in the 1950s, and that is creating artificial constructions that think in terms of modeling of how we think. And we have finally gained enough computational sophistication to actually do that. And you can see that just as we learn over time, just as a child eventually will see enough pictures of a dog or actual dogs to know something's a dog, that's the exact same thing and the way machines are learning. All right? And of course, there are short-term practical benefits for this in our industry. Bots, natural human language interface. You can probably think of data analytics and many, many more. But the long-term implications are fascinating, right? When you can have machines that genuinely think and can do work. I mean, think about the economical implications, the ethical implications, and so forth. All right? Okay, and just one thing. So we're going to be hosting another event that is going to be really fun. This is in July. I'm going to give a talk on computer chess and how that's been a roadmap for machine learning. But here's the fun part. A friend of mine is the youngest grandmaster in Canadian history. And so after we do the talk, we're going to set up 16 boards in the office, and he's going to play 16 people concurrently. It's a really fun thing. So if you want to watch a grandmaster cream a bunch of novices in chess, or you want to be one of those novices who gets beaten, please contact our Infusion people at the back. Yeah, right here. Bring it. Okay, thank you guys, and I will open it up for any questions.